Right. Do you like, love, like, Okay.
I'm going to hold you responsible to it.
I'll hand your exams back a little bit later at the end of class, and then if we have time, we might go outside. I want to show you something.
Oh, you brought your pair on?
I brought the mirror. Yeah. We did it yesterday. I almost put my eye out with the thing. It's a little scary.
Yeah, I'm guessing you probably did this.
Well, I didn't look into it. I was just sort of moving it, and I just felt this very hot patch of light go across my face.
Wow.
That was probably
I almost singed all day.
Huh?
That was probably very fun and exciting.
Right. It's not nearly as scary as one day we were doing this solar observing at the middle school here in town, and I was just in a hurry, and I just wasn't thinking, and I had the telescope all aligned, but I couldn't find the sun. And we have a solar filter on the telescope, right, which we keep on there. But sometimes you take it off, get it aligned, and then you'll take the eyepiece out and you'll put a piece of paper on there until you find the sun on the screen of the piece of paper.
You almost put a piece of paper on?
No, I had the piece of paper, and then I put the eyepiece back in, but I forgot to put the solar filter on. And then I started looking in the eyepiece, but it just was, I couldn't find the sun. You know, thank God I couldn't find it, because if I had it, it would have put my eye out, or it would have probably damaged my eye for life. So it's very bad to look through a telescope. And then like 2 minutes later, I was like, oh.
That was a close one.
Was close, yeah.
Like 2 times in the last 2 months, I almost killed my, or
All right.
caused permanent damage to myself.
Let's look at the mirror equation. Let's see, we've sort of been over spherical mirrors, concave and convex mirrors. Is that right? Yeah. Let me show you this mirror first of all. This is a, I know what type of mirror this is. Right, this is a concave mirror, right? This is the type that sort of caves in. So if you look, you see yourself in this thing? Yeah. Yeah. How do you look? You're upside. You can see yourself actually. Now, if you look really close, you get big. You're big, right?
Yeah.
Okay. The focal point is right about where Chow is right now. The focal point's a little less than a meter or so. But if you move back, can y'all see yourselves more?
Oh, I can see somebody else.
Can you see yourself? You should all look upside down, right? You're upside down? Yeah. You see, Joseph? Was it?
Yeah.
Yeah. You can do this with a makeup mirror.
I see sorry, Jose.
Okay. Y'all can see yourself? Wayne? Yeah. These are pretty cool mirrors. I just got it. But the focal length of this is about a meter or so. Remember the focal length we define as half the what?
Image.
Half of what, John?
C.
Half of C, right? Half the radius. So if you imagine this being a sphere, it'd be a sphere a couple meters in radius, right? This is just one small part of the sphere. And the focal point, if we take it out, like for example, we run this bit and focus the sun at a certain point, the rays of the sun will focus at about here. Right? Yeah.
If you put that in front of the projector right there, would it give a backflip image to the other wall?
Yeah, you'd have to set it up just right. I'm not sure where exactly.
Okay, I'm just curious about it.
But
Try.
yeah, you could do it. I don't know exactly where to put it right now. I have something else for you. You can pass this around and sort of play with it.
More things.
This is also a concave mirror. There are actually 2 of them. So you can, if you want, you can take it apart and you can put your face up here. This is like more of a...
Blind yourself.
No, you can't blind yourself, but you can see yourself really well.
If you want to see something kind of cool, there's a video by Vsauce in which how would you look in a spherical mirror?
Okay, I'll take a look at that. But, and then you can also put them together. There's a little pig here. Put it on top. You ever seen one of these? Kids love this.
It looks like infinity.
Now you look, if you look down in, you can see the pig, but if you look at it from right here, it's like the pig is right there. So this is a type of real image. It's a little bit different than a real image because you're not projecting it onto the screen, but it's more like a hologram. So you can oh, it's right there. Kids, like, they always freak out, like, that's right there, and then they can't touch it. Right? You can take it apart if you want to look into the actual concave mirror.
I remember whenever we went to Florida, I think it was in Kansas City, we went to Ripley's Believe It or Not, and they had something like that, a little gym, but it was supposedly that if you got your hand, it would cut off a laser, and it would set up a alarm, and I was like figuring out a way to like grab it.
Mm.
I know it's fake, but
Right.
suckers, I got it.
All right, so anyway, with the mirror equation, we have this expression, 1 over f is equal to 1 over p plus 1 over q. If y'all are in the lab, I know all of like 1 or 2 of you are in lab, you've used this already. Y'all done the thin lenses? You done thin lenses yet?
Yep.
Yeah, this applies for mirrors and for lenses. F is the focal length, P is the object distance, and Q is the image distance. Remember those signs, right? That Q is going to be negative if it's a virtual image, and F is negative for what type of mirror? Concave or convex? Oh, we haven't gone over that yet? Okay, we'll see that in just a second. Oh, here we go. So, what is the focal length for a flat mirror? Can you imagine what that focal length is? Now, if we imagine that we have a concave mirror and the focal length is here, what happens as we flatten that concave mirror to the focal length? No? It gets bigger, right? As we, like if I have a concave mirror that's taken out of a sphere like this, that sphere has a certain radius. But if I have a flatter concave mirror, it comes out of a much bigger sphere.
Unless it comes flat, it don't.
Right. So if I have a concave mirror that comes out of a sphere like this, it has a certain focal length. But if I have a concave mirror that comes out of a much bigger sphere, cutting it off, it's a flatter concave mirror, right? It's spread out a bit. So the focal length then of a flat mirror is going to be infinity. So the focal length of a flat mirror is infinity. Or it approaches infinity, to be more correct. And if we look at the equation for flat mirrors, it also holds true. 1 over f equals 1 over p plus 1 over q. And remember for flat mirrors, p, or rather q, is equal to negative p. And so if we just put that in here, we have 1 over f equals 1 over p plus 1 over negative p. So 1 over f equals 0. So f, in order for that to be true, f approaches infinity. That's for a flat mirror. Now, there are some sign conventions for our variables for these. Some of these we've talked about. If the object is in front of the mirror, then I have a positive image distance. That's sort of the normal way of things. We'll see later when we do combination lenses, when you have two lenses next to one another, where you can have your object in the back of the mirror. That means this would be called like a virtual object. We'll see that a little bit later, and you probably saw that in lab. I'm not sure if y'all do that. But this is called a virtual object. As I said, that will come later. The image distance, as we've talked about already, if the image is in front of the mirror, that means that you can project it onto a screen. It's real. If it's behind the mirror, it's negative and it's virtual. And then those things we've already seen before, except for the virtual object. But now the focal length. Now, if the focal length is in front of the mirror, as it is with this mirror, when I say in front, I mean that the focal length is on the same side as the object. So if you imagine the focal length of this mirror is, right up here. That's in front of the mirror. As opposed to a convex mirror, where if I were to imagine this is the mirrored side that you look into, the focal length would be behind the mirror. Follow what I mean by that? By in front and behind? In front would mean like the side where the object is. So if my focal length is in front, it's positive. This is for a concave mirror. If it's behind, it's negative. That's like for a convex mirror. Concave and convex. I won't tell you in your problems whether the focal length is positive or negative. You'll just need to know, well, concave has a positive focal length and convex has a negative focal length. But whenever you're using the mirror equation, you have to get the sign correct. Because
The object is here.
Let me show you. So this is a convex mirror, right? And the person stands over here. If the focal point was in front of the mirror, in the way that we're describing it, the focal point would be right here. Right? But the focal point's not there on a convex mirror. Right? Because we're imagining this is coming out of a larger sphere, and so the focal point is right there. This is my focal length for a convex mirror. And that focal point is behind the mirror. It's not in real space, it's in the virtual space behind the mirror.
I don't grasp that concept. I don't know. For some reason, it doesn't make sense to me. I mean, I see what you're saying.
Right. Just physically, like it's on the opposite side of the mirror.
The focal point's here. So the okay, so if the rays are coming off of him, how do they go into that?
Oh, we'll see that soon. Yeah. They're not actual real rays that are crossing. They're virtual rays. Just like we had with the flat mirrors. It wasn't the real rays that were crossing. They were. We traced them back. We call them virtual rays.
So is the focal point with the radius or convex and convex?
It's half the radius. Yeah.
Oh, it's half the radius.
Half the center of curvature. The center of curvature is the radius for a spherical mirror. All right, so these sign conventions are very important when you're working through some of these things. With practice, you'll get them, but you also just need to study these and make sure you know them. Usually students, this is the trouble that they have, are the sign conventions. Let's try this. This is a fairly straightforward problem, but concave mirror has radius of curvature of 20 centimeters. The object is located at 20 centimeters. What is the magnification? And then I'll be right back. All right, try to wrap this up. 10 more seconds. All right, I'll stop at 2:35. All right, we're sort of all over the board. B, C. I'm not sure what it is right off. Let's just see. So first of all, our radius of curvature is 20 centimeters. And what that tells us is that the focal length is 10 centimeters. All right? It's a concave mirror, so that tells us that this is a positive value. The next thing it says the object is located at 20 centimeters, so that means our object distance is P equals to 20 centimeters. and I want to know the magnification. I know the magnification is negative q over p. All right, I have p, so I just need to find q. So I'm going to use my mirror equation. 1 over f, that's 1 over 10, equals 1 over p, that's 1 over 20, plus 1 over q. And I solve this for q. That's 1 over 10 minus 1 over 20 equals 1 over q. It's 2 over 20 minus 1 over 20, that's 1 over 20, so q is equal to 20 centimeters. All right, so then I can find this magnification. It's equal to negative 20 over 20, which is equal to negative 1. All right, so there are some things that I can describe this image as being. C was the right answer. Is it real or virtual, this image? It's a real or virtual image? It's a real image, right? What of them tells you that it's real? Something is either positive or negative. What is it?
Image distance.
The image distance. So it has a positive q, which I were thinking, if you thought it was virtual, is probably that the magnification is negative 1. Is that what you were thinking? But the negative magnification tells you what about the image? It's upside down. So it's a real inverted image. And we know it's inverted because it's a negative magnification. And is it bigger or smaller than the object? It's the same size as the object. Right? We know that because the absolute value of the magnification is equal to 1. So it's the same size as the object. We'll see this when we do ray tracing diagrams. There are several different scenarios with mirrors and lenses where you can get different types of images. You can get real or virtual images, you can get inverted or upright images, and then your images can be the same size, big or smaller, bigger than or smaller than the object. But they all fall out in the math too when you actually calculate these various things. Let's try another example. We haven't done ray tracing diagrams, so I'm going to give you a little bit of a jump start here. I know a couple things about this. One, that the image is upright and that it's smaller than the object. So if this is the object, and then there's some mirror right here, a type of mirror that I don't know, flat, concave, or convex, and then the image is back here. I don't actually say that. I don't say that it's behind the mirror. But the reason that I know it's behind the mirror, don't worry, we'll see this with ray tracing diagrams. It's behind the mirror because it's upright. All right? That tells me that if it's upright, that my magnification is positive. And if my magnification is positive, that means that I have a negative Q. All right? So because of that, I can say that it's a virtual image. Because it has a positive magnification, it must have a negative image distance. Wait, did I say that it has a positive magnification? Don't worry, we'll see this with ray tracing diagrams. There are only a handful of scenarios. All right, so what type of mirror is this then? Yeah, Jose?
Question. So, in that scenario, the object looks bigger in front than it's in the back.
Right, the image is in the back of the mirror, and the object is in the front of the mirror.
But aren't you saying right there that it is 20? Never mind.
Right, so
maybe,
this...
Maybe I'm getting confused by the way it's worded.
This distance is 20 centimeters. All right, what type of mirror is this that produces an image like this? It's not a flat mirror because the image is smaller. It's a convex mirror, right. So the type of mirror that produced this image is a convex mirror. We'll see this with ray tracing diagrams. Don't worry about it right now. But convex mirrors are the only mirrors that produce an image that is smaller and upright than the object. All right. Concave mirrors will produce smaller images, but they're always inverted, the smaller images. If they're upright, they're always bigger. All right. So with that information, go ahead and answer these other questions. I answered the first one. And as I said, we'll sort of feel that out when we do ray tracing diagrams. I'll give you a bit of a head start, then I'll jump in. Does somebody have a magnification for me? Right, yeah, 1/2. Yeah, you're right. Yeah, so height of the image is 1.5 centimeters. Height of the object is 3 centimeters. So the magnification is equal to positive 1/2. We know it's positive because it's upright. Do they have a Q value for me? 10. I can come here. But it's not 10 actually, it's what? Negative 10, right? So from this I can say Q is equal to negative M times P. Now that I have M, I know P is negative 1/2 times P, which is 20 centimeters. That's equal to negative 10 centimeters. All right, this tells me that it is a virtual image. And so the magnification is plus 1/2, negative 10 centimeters, and now I just want to know the focal length. I already know that it's a convex mirror, so that focal length should be what? Positive or negative? Negative, right. Anybody have a F for me? 60, let's see. So F equals 1 over Q, 1 over P, the inverse of that. What's that? Negative 2 over 20. Negative 20, right? What y'all got? All right. No, remember the other one was a concave mirror, and so the numbers are similar except one of them's negative, right?
Yeah.
So yeah. Or the negatives are switched, I think.
So last time Q was positive, right?
Right, but
Oh, this one is negative, so this should be good, I think.
so anyway, F is equal to negative 20. That was pretty basic, but you could see something like that on the test. However, sort of the hard part in these questions is this first little part that I helped you with, figuring out what type of image it is, what type of mirror it is, and knowing the signs of the various things before you ever actually get started on the problem. You'll get a feel for them. We're going to go through all the ray diagrams. There are only a handful of scenarios. I think you'll get a feel for them. So Memorize sure if you have to, but otherwise, I think that you'll just know them. Like you'll know them. All right, let's do this one more clicker question, this multiple choice one, and then we'll go outside and do this thing.
Things on fire.
Yeah, I thought we could do it inside, but it might set off sprinklers or something. So we're not going to do that.
It won't. Sprinklers are heat. They're heat. That's why whenever you if there's a fire, the entire building doesn't get soaked. It only breaks the ones above it. They're all heat because if you actually look at them, there's a little glass vial that whenever it gets beyond a certain heat, it'll break, and then they're always under pressure.
Okay, well let's do this right here.
Or you know.
I'm just going to write down what we know here. Let me show you something here that I've written that you might not have known right off, is that the image height is positive. This is a concave mirror, and you're bigger than the object. The image is bigger than the object. So that's like the shaving mirror. You hold it really close to your face, right, and you look bigger. You'll do that in your bathroom or whatever. If you hold it really close to your face, you look bigger, and your image is upright. Right, so our image height here is going to be positive. Again, that'll come with the ray diagrams, and we'll see that next time. Thank you, Scott. I got it.
Can I see something real quick?
No, you can go back to your seat. Thank you.
I'll see if I can see it.
All right, try to wrap it up. Thanks. 10, 15 seconds. $3:35. Stop. It's 5 more seconds. 3:35. Let's see, B. That must be right. So here, I have some information over here which we sort of come about just from reading the problem, but also knowing the different types of images that these things form, which, as I said, we'll see next time when we do the ray diagrams. And then I can just say HI over HO is equal to negative Q over P. And then we solve this for Q, which is what we're looking for. So Q is equal to negative P HI over HO, that's negative 3 times 2 over 5. 3 times... Was it B? What did y'all put? No, it's C, right? Is that right? That's 0.4. 3 times 0.4. Did I do something wrong here?
Why did you find M and then just find Q after that?
You could do that. Did I do this incorrectly? Oh, 5 over 2. It should be HO over HI. Oh, 5 over 2. Yes, you're right. I'm wrong. 5 over 2. Alright, so that's 7.5. Or negative 7. Alright, we'll do these others next time. And we'll move on. We'll do the ray diagrams. And then we'll also do move on to thin lenses. We only have a few more classes. I'm not sure if we're going to get to Chapter 8. We'll probably try to get part of Chapter 8. But I don't know. We'll see. We'll just sort of get what we get. So this semester we've really run short. We usually have plenty of time at the end of the semester. And I was hoping to add some other topics, but these exams.